We would like to apply Faraday's law to the following problem. Let's consider a solenoid, and I'll just make a sketch of my solenoid over here. So we're wrapping the solenoid with wires, and wire coming out, wire coming in, radius r. And what I'd like to do is run a current into the solenoid that's changing in time. And what that means is that inside our solenoid, and this will be a very long solenoid, so that our field lines will point along like that. And what we expect here is that when I'm changing the current in the solenoid, the magnetic field in the solenoid will be changing in time. And we know from Faraday's law that that means that while the magnetic field is changing, there's an electric field everywhere in space. And that's what we'd like to calculate. So let's just look again at this picture from an overhead view. So we'll draw, this is our overhead view. And our solenoid has a radius r. And our magnetic field is coming out of the plane of the figure like that. And what we'd like to do is say that di dt is increasing. So our current in the solenoid is not constant, but increasing. And what we'd like to do now is calculate the electric field that's induced everywhere in space. Now, there's two regions of space. So let's call this region 1 and region 2. So our region 1 has r less than r, and our region 2 has r greater than r. And now I'm going to apply Faraday's law, which says that the line integral of the electric field around a closed path, and this closed path we're going to call our Faraday loop, that will be equal to the change in magnetic flux through a surface with that loop as a boundary. And this is the law that we'd now like to apply. So when applying Faraday's law, the first thing we want to do is let's consider our first case, r less than r. We want to choose a Faradayan loop. So I'm going to choose a circle of radius r. And I do have some prior knowledge that by the symmetry of this problem, our induced electric field will be a tangential field. And remember, line integrals are either 0 if E is perpendicular to the path, or it will just be E times the length of the path in the symmetric consideration when the electric field is tangential to the path. And that's why I'm picking a line integral like that. Now, where we're going to consider our flux is through this surface that I'll mark like that. That has the path, the Faradayan loop, as our boundary. And we'll just, again, illustrate that with an FL. And now the crucial thing is to calculate this magnetic flux. And recall that this is an open surface with a unit normal. And to make our calculations straightforward, I'm going to choose a coordinate system in which my unit normal is pointing out of the plane of this figure. And because of that, that means the circulation direction has to correspond in this manner. So that's going to be my circulation direction on the line integral here. Now we want to compute. So the flux is just, this is minus d by dt. The B field in the solenoid is uniform. We've seen that in our Amperian law calculations. So I just get B, and the area is pi r squared. And on the left side, here we have E times 2 pi r. And this law is equating these two quantities. They're quite different. I equate them by the physical law. And I can see that I get an electric field that's equal to minus dB dt times r over 2. Now, recall, let's just remind ourselves very quickly that if we wanted to do an Amperian law calculation, and I have my current going like that, as the solenoid is wrapping around coils are wrapping around. Then I'll choose a little length L. And from Ampere's law, the integral of B dot S is mu naught I enclosed. And over here, there's only a contribution along the inner leg. Recall that the B field outside a solenoid, infinite solenoid, is 0. So this is a very long solenoid. And on this side, how much current goes through? Well, if I have a number density of turns, this is the number of turns per unit length, then I have little n, my length is L, times the current in every turn, and I get my B field is mu naught n times I. Now, the electric field depended not on the B field, but on the change in B field. And so we see that our electric field is minus mu naught n di dt. That's the B field, R over 2 for R less than R. And so what we see here is that if the current is increasing, that tells us that our flux B from the B field is increasing. And so we should have an induced current. Well, we should have an electric field that is opposing that change. And so we'll examine that in our next calculation.